mode. Okay, and then I shall share my screen. Let's first move on to guess this. Okay, I think we should get started. Great to see all of you. We had quite a lot of things going on here. So earlier this week, we offered the first AI workshop on campus to open to all WashU students and faculty, and we had an amazing turnout. There were about 140 people at WashU registered for the workshop, and about half attended the live session, and another half watched the recordings. So presumably near everyone who registered have participated in the workshop. So this is a great turnout, and we'll keep the momentum. Yu has been instrumental in helping me designing the presentation slides, the workshop materials, and we'll continue this effort. The next AI workshop has been scheduled on March 19th, and right after the spring break, and we'll be talking about AI detection tools for writing, which is definitely a very hot topic and very controversial topic. So if you have time, I would highly encourage you to attend the live session. So you can post questions, you can go along with Yu and me, surveying those topics. But I know some of you are overseas and cannot attend the session, the live session. Then we'll have all the AI workshop recordings ready and released on YouTube. So feel free to watch the YouTube videos if you cannot attend the live session. Okay. Okay, so medicine has been going on in the field of AI. Not to say the Sara model, which OpenAI made, that has this amazing capacity to produce photorealistic visuals, based on text prompt. But I don't think the model has been publicly released, so probably we are going to wait for a while before we can tap into the model ourselves. So today we are going to switch gears. So in the past few weeks, we have been talking about mainly large language models. We have a number of presenters in our group who introduced you various aspects of large language models regarding, for example, how you can fine-tune it, how you can prompt engineer it, how you can build tooling on top of large language model. But today we are going to switch gear and revisit the computer vision model. I think it has amazing capacity, which may be underutilized to some extent. So I recently found out that the Huggingface, which is the #1 platform to host open source AI models, have provided this amazing tutorial, really demystifying the use of the SAMS model. So we are going to go over that tutorial together. I think it's very hands-on, and basically you can use that as a template to either use the SAM model out of box, or you can actually fine-tune your own version of SAM model, which is I would say it is truly truly powerful. So just remind you what SAM's model is. SAM's model is the abbreviation of segment anything model. As you can see here, it is an open source model developed by Meta. So although, well, a lot of people criticizes Meta or Facebook for social media contamination, all that. But I have to say, in open sourcing their models, Meta is at the lead, right? So recently you've heard that Google finally decided to open source their large language model, JAMA, which is a derivative of their closed source model, Gemini. So following the lead of Meta, so Meta has always been a pioneer in open sourcing their models, and of course they spend millions of dollars in training those models. It is really a service to the AI community for them to open source those really powerful models such as Llama, Llama 2, and recently SAM model. So SAM model, if you take a look um, of the frequently asked questions, it is trained on huge amount of data. It's trained on the 1 billion image data set that allow us to basically segment anything from an image. Segmentation basically means that getting a mask from the image so that we can, from an image, we can say segment, this dog or that dog, or maybe the background, the ocean, the sand, etc. Right? So, and all this has been done automatically, so out of the box. So for a majority of the tasks, you won't even need to train the model because the model have seen 1 billion images, of course, annotated images, to be able to accurately identify objects from the image and automatically segment the image, maybe providing a mask of the object, all the object in the image. Right? And another key feature of SAM's model is that it allows prompting. It's not the traditional way we think about prompting in large language model, because in large language model, we need to, we write text, right? Maybe asking a question to the model. So for prompting in SAM's model, mainly we are either providing a point to allow the model to identify an object. Maybe, if I put a point on the eye of the dog, the SAM's model will be able to tell, actually, I'm going to segment the eye of the dog from the rest of the image. Or we can provide bounding boxes, right? We can provide a rectangular box so that the model knows exactly what I'm looking at. And maybe I'm just trying to segment this this light color dog from the other dog and the background. Okay. So that is what we mean prompting in SAM's model. So of course, actually, we could it won't be too hard actually to figure out a way to use text prompting in SAM's model. So the out-of-box SAM's model doesn't actually have any labels. So the model doesn't know which one is a dog, which one is an ocean. It just tries to segment everything, right, from the image without actually knowing or identifying or labeling any part of the image. Okay? But by combining the SAM's model with other image object detection models, such as EULO 8 version, we probably would able to do that. Okay. But today, we are mainly just talking about the capacity of SAM's model alone. We will see how we can use the model out of the box using prompting, and also how we can fine-tune the model on medical images. Okay. So some interesting facts about the SAM's model. For example, the original model was trained for 3 to 5 days on 256 A100 GPUs, right? So that's cost a lot, right? So some of you know that the A100 GPU produced by NVIDIA is quite expensive, probably at $100,000 a piece, right? So I don't think any one of us would have 256 A100 GPUs in our warehouse. I don't know even for WashU we have that many 800 GPUs. Okay, so training the model is not a small deal. So currently, the model size actually is quite modest. The model has two parts. One is the image encoder, one is the prompt encoder and decoder. And the image encoder has only 632 million parameters. Well, I say only in comparison to large language models, which have billions of parameters, right? But well, for for image model, I would say the size of the model is quite modest. It can very much fit into a single GPU for making inferences and fine tuning. So that is actually key because we know if the model is too large, then we won't be able to handle it with a single GPU. And most likely we cannot fine tune the model at our end. But actually, because of the relatively small size of Sam's model, it's quite doable on a single GPU, and we'll illustrate that using the Google Colab. Okay. So any questions, any comments before we get started to the Colab session? We're all good? Okay. Okay. Yeah, no, thank you for the comment here. Yeah, so yeah, I would say Yu is definitely the one who take all the credits because she designed, no, I just gave her the topic and she designed all the materials and went over together. So yeah, I think it's definitely very helpful information for students, actually not only students, but faculty as well. Okay, so thank you for the comment. Okay, so let's move on to the tutorial. So I largely just borrowed tutorial from Huggingface. If you are familiar with Huggingface, I would highly encourage you to be familiar with it because it's is one of the probably most amazing platform for open source models. Okay, so it hosts probably up to 500,000 AI models now. And you can take a look of all the model categories, right? And they have many foundation models hosted there that you can use. You can test on that platform. You can download. You can fine tune. You can use the model. You can host your own version of the model. And in my deep learning, we had several lectures focusing, actually 3 lectures focusing on Huggingface. But if you have not taken my course, I would highly encourage you to go to Huggingface, and they have a lot of teaching materials there that you can self-learn. They have documentation, community. Where is their course? I remember they host some courses in Huggingface as well. So see, they have a leading board, which show the most. See here, the Google JAMA model, 7 billion. They also have a 2 billion version. I haven't really tried that out, but it seems to be pretty powerful. I couldn't really see there. They have just a lot of materials there. I don't see their courses, but they have some courses that you are free to take. Maybe no UE, maybe you maybe in the learn. Yes, here. There's NLP course, deep. This is a reinforcement learning course. I haven't really take a look of this course, but yeah, they have tons of cookbook that you can use. Yeah, basically, I would encourage you to go here because the Huggingface is mainly a platform for hosting natural language processing models. So it has its own ecosystem. So I would highly encourage you to learn this one. You have to start from the very basic to relatively advanced topics. Okay, so a lot of learning materials. But let's move on to the SAMS model tutorial. And as I said, I largely just borrowed the tutorial, and I did run all the 4 tutorials on my single A100 GPU using Google Colab paid version. If you use the free version, I don't think you have access to A100 GPU. You may have some T4 GPU. It's going to take longer to run, but it's still quite doable. Okay. Okay, so let's get started. Here you can first download the transformers because we are going to use the SAMS model that is hosted by Huggingface. Okay, so it's going to be the Huggingface version of the SAMS model. So therefore, you do want to install the Huggingface package, and it's called transformers. Okay. And then there are some utility functions. Those functions are quite easy, but they are basically allow you to either show a mask of the predicted mask, or show bounding boxes, or show points on an image. They are just some helper functions. Okay, so we will use all the functions later on. But well, those functions are written already by the transformer team, so we don't need to recreate the wheel. Okay. Model loading is very transparent. But making sure that you use your GPU, right? So if you click runtime, I think it's runtime, right? So you could, where is my change runtime type? You can choose, if you use free version, I think you could only use T4 GPU, but if you use the paid version, you may be able to access V100 GPU or A100 GPU. So A100 is the most advanced GPU, not the most advanced GPU ever built. Now they have this H200, which is probably 10 times more powerful than A100, but A100 is pretty powerful already. Okay. And so basically you download the model and you also download the SAM processor. Okay, so you do need both. And you can see here, well, is by Facebook. Okay. So as we said, the model is quite small, so it doesn't really take a lot of space. It's only 2.56 G, so it's quite modest in size. And then we can load a sample image. So this is a sample image. You can load whatever image you want. And we just open this image. This image is you can say it's a truck, a car, a vehicle. Okay. And we are going to show a few though probably all of the key functions of SAM's model. Okay. So the first step is to before we can show the use cases, first step is to retrieve the image embeddings. Okay. Because well, very much like the large language model, the image, the SAMS model also embed the images. Basically, embedding is just representing the image using vectors, okay, a vector of floating points. Okay, so we have to embed the model, embed the image. we call the processor, and then we use the model weights to embed the image. Okay, so basically we are calling the embedding layer of the model to embed the image. Okay, so that we convert the pixels values into floating numbers. Okay, that the model can make predictions. And now let's take a look at the first use case, which is to feed a set of 2D points to predict a mask. Okay, so basically what I'm doing is I'm going to use the helper function to pinpoint somewhere in this image. For example, here, this is the backseat window, right? Or the tail window. Okay, I'm going to just use no the x-axis and the y-axis to pinpoint this point, which no is at the tail window. Okay. You can provide multiple points. So here we just provide a single point, but making sure that these points have 3 dimensions. Okay, so this is a rank 3 array because well, consider image. No, you need to have a channel dimension, right? Which denotes because it's an RG image, it has 3 channels, right? The red, green, and blue. So the first is the channel, the dimension of the channel, and then the height, and then the width, right? So therefore there are 3 dimensions. So therefore you do need to have 3 brackets to represent the 3 dimension. Okay. And then well, you can show these points on the image is here, okay, using this helper function. Okay. Pretty straightforward. And then let's see, no, this is the prompt that we provide, right? And based on the prompt, we are going to provide those prompt, basically the input points to the processor here, okay? And then we just ask a model to make a prediction. Okay, so you are already familiar with this. So this model is basically the SAMS model, and we just provide the inputs. Okay, the inputs is just the single point that we used as a prompt. And then we can harvest the masks provided by the model. So by default, the SAMS model is going to provide 3 maskings. Okay, why 3? Well, because sometimes the SAMS model, I'm not so sure which masking works for you the best. Okay, because when you pinpoint a point here, you may want to get just the tail window, or you may want to get a larger area, or you may want to get the entire car, right? It's not entirely clear which masking you want to have, right? So therefore, as the default, SAMS model provides you 3 for to choose from. Okay. And each masking is associated with score, but I would say the score is not that useful. It's really your decision, right? Which one you want to take? Which do you want to take? No, I'm more interested in this tail part of the tail window, the entire tail window, or the entire part, right? So yeah, so just by going through the model, you get 3 maskings. Okay, and the maskings basically is just the same size as image, but with 0 and 1s. Okay, 1 just means the area that is in the masking, whereas 0s means out of the masking. Okay, very simple idea. Any question? Okay, good. And we can also try 2 points, right? So here, instead of providing a single point, we provide 2 points. One at the tail window again, and one is at the front tire. And we go through the same process, okay? And now it provides 3 maskings, and all 3 maskings are about the same, relatively the same, and they cover the entire car, right? Which is not surprising because most likely you want the entire car because one masking is at the front, the other at the one at the back, the other at the front. So it's following like a diagonal pattern. So very likely you're going to get the entire car. So therefore, this masking provided. Again, 3 maskings. They are probably tiny bit different. You can take a look, right? So this one, it doesn't really cover the very back of this car. This one covered probably more. So there are slight differences, but no, about the same, very similar. Okay. Okay, so that is no, the first prompting, you can use either single point or multiple points to identify the masking, to prompt for masking. And the second use case is to predict the segmentation using bounding boxes, which we are most familiar with, right? So because in object detection, what we are doing is basically using the model to identify objects and use bounding boxes to identify the location of the object in an image. So that's create a bounding box. The bounding box is created using 4 numbers representing the first number, 650, representing the top left, and 900 represent no, sorry. The 650 and 900 represent the top left point, and 1,000 and 1,250 represent the bottom right. Okay, so because the bounding box is always a rectangular shape, so that as long as you identify 2 points, the bounding box is identified, right? 2 points at the diagonal, so you can define the bounding box. Okay, and the bounding box is here. Okay, and in this case, well, we are just trying to grab. Most likely, the idea is to grab this tire, right? The back tire. Everything remains the same. We provide the bounding box instead of the single point. We provide the bounding box to the processor, and then we call the model to make a prediction, but making sure that you use this torsional grad because we are not going to update the model. We are not going to calculate the gradient of the model. So all the weights of the model are fixed. We are just using the model as a gigantic mathematical formula to make a prediction. Okay. And let's take a look. So there are, again, 3 maskings are provided, and they look really similar. There are probably very slight differences that I couldn't even tell with my eyes, but yeah, they are slightly different. It's really up to you which one you want to choose. Okay. Any questions so far? Okay, good. And then the third use case is we can use both the bounding box as well as the point to identify masking. Okay, so here we provide a bounding box as well as a single point. This point is in the middle of this tire. So why we want to do this? This is because we want to carve out an area in the identified object. So that's what I mean here. Okay. So when you provide both the boxes and input points and make the predicted masking, you see that in the middle, let's see, this is clear. In the middle, actually, it carves out this area. You see that this is it's hard to see, but this is like a green area. So this area is being cut out. So basically, you just get the tire, but not the middle of this tire. Okay. So this is one way that you can carve out part of the object out of the scene. You can also actually try out using a bounding box here. You'll get a similar effect. Basically, the middle is going to be cut off. It's not going to be included in masking, but the surrounding area, so this area, are going to be included as the masking. Okay. So this could be useful if if you want to make this very fine refined way of getting an object that is not a regular shape. Okay. What else? Yeah, you can also pass uh let's see. Oh, okay. So this part is interesting. You can pass points with a label to segment out a region. Okay. So here we provide the boxes, the input, and also we provide a label. And so we provide here the both boxes and inputs and label. And then we provide the labels here in the processor. And what it does is provide three maskings with different sizes. And each size a little bit larger, including just this labeled area, or expand on this and expand on the entire bounding box area. Okay. So well, actually, I don't know exactly how much useful it is, but it's you have these options. Okay. So providing both bounding boxes, endpoints, and labels to the model. Right? And you have gradually increasing areas covered by the label alone, covered by the surrounding area, and covered by the entire bounding box. Okay. What else? Predict multiple masks per image. You can definitely do that. You can use either multiple bounding boxes or using multiple points to identify multiple places. So here we use 2 points. And then the predicted, where is the let's see, we provide these 2 input points, and yeah, there are, which one correspond to which? Oh, okay. Actually, they provide a total of 6 maskings. So this one and this one pertaining to the points at the back tire, and the 3 pertaining to the points identified at the front tire. Okay, so they are going to basically for each point. For each point, they are going to produce 3 maskings. Okay, so a total of 6 maskings. So in this case, you're going to do things a little faster, right? You won't have to go through each time, provide a single label. You can provide multiple labels, so it's going to provide multiple masking for you. Okay. You can do the same trick by providing multiple bounding boxes, and then you are going to get multiple images maskings for both the back tire and the front tire. Okay. Any questions so far?
Yes, I'm curious about the label. If I use the label, it will help you like ignore the components. But I think like if we take a look at the label, it only changed the green point to the red point, and the label like equals to 0. But I don't know which the label is.
Let's see.
Yeah, it's the label. It's just the label equals to 0.
So here, let's see.
Like what label is input and to like what?
Right. Let's see. We provide these labels as let's see whether we have a description about this. Mm. So here we have a bounding box, we have the input, and we have a label. So this label 0, I'm guessing that this label 0 pertaining to the bounding box. So this would be label 0, this would be label 1. But I haven't really tested this. So this I just borrowed their lecture, their tutorial. I'm guessing that probably this label referred to the bounding box, but let's see their prediction. So
It said, as you can see, the model managed to ignore the
ignore the component, yes.
at the point with the label 0. It's like the point is the red point, and it's the label.
We can't really see clearly how that's been handled. Hmm. Yeah, it's not really clear to me, yeah, how they handle this. I was already thinking that they just make, you know, 3 different one is smaller, one is larger, but actually it says that the model is going to manage to ignore the component that was specified by the point with label 0. But label 0, I'm guessing, is just the bounding box. Yeah, that's interesting. We have to probably look deeper into this. It's not clear from the image that how they ignore the label, ignore the component specified by the point with label 0. Um, okay, so yeah, we'll probably look deeper into that and do some experimentation. Um, So yeah, we'll probably discuss this next time. We have to rerun some code here and play around with label a little bit to get to know exactly what the label is doing here. But at least just observing the image here, I don't see they've been carved out. I think this part is definitely carved out. So uh, when we provide both bounding box and then in the bounding box we have a point, I think that is where we carve it out. But yeah, so I'll play with the code a little bit more to
Is that interesting?
understand more about it.
IXGPT, what its label equals 0 means in like segment or CV task is that the label
Mhm.
0 is often reserved for the background because it's the default or base category against which
Yeah, that's possible. Yes, that's right. That's right. For image segmentation, usually label no, we label background is 0. Yes, that's true. But I don't know exactly how this play a role here. Definitely is I don't think it's really getting rid of the background. I don't see how they did that because if they clear out the background, we are going to see the opposite. Basically, they carve out this part from the background. Yeah. So I don't know. We have to experiment a little bit more to understand this. Okay. Um, so I think in reality, we really don't need or don't really use this two outer box to do segmentation because well, it's a little bit I would say hacking to know just from the image, well, know which point actually because you have to provide those points, right? Very precise bounding box or point, which could be hard, right? From the image, you would say, well, is this part, 1,500 or 605 500, it's really hard to say, right? So we usually use some software, usually commercialized software to draw bounding boxes or just tap onto the image to get the points. Okay, so seldom we are going to use this way, but I think it's good to understand the prompting of the SAMS model because that is coming out of the box. Okay, it's actually how these models were trained. Okay, great. We'll come back to that, to the label part, and probably experiment with it to understand more. Okay, and the second part, this part is pretty easy. Is automatic generating all the masks, right? As we said, the SAMS model has the capacity to identify all the maskings out of the box. We don't actually need to provide any label. If you don't want to provide label, you can just allow the model to identify all the maskings simultaneously. So you install the transformer, you have the utility function, everything remains the same. So here we have an example image, right? And here basically you just allow the model to generate all the masks. Okay, very simple. You use the generator, which basically you call the model and then you provide the image. And then basically it take about 7 seconds. Actually, even I tested probably 3 seconds, I would say, to generate all the maskings. Okay, and you showed all the maskings here, but actually, what it does is just providing. No, if you take the length of the masks, there are 138 masks being produced. Okay. So the number of masks really depends on the complexity of the picture, right? So this picture is pretty simple, but it still is identifying a large number of masks, right? Because if you have a very complicated picture with a lot of objects, then you are going to have probably thousands of masks. Okay. So, and each mask, so let's take a look of one of the masks, okay? One of the 138 masks. And you will see that most of the values in the vector in the mask are false, this is 0. But not all of them are 0. So if I count, there are 21,941 true. Basically, that may be identified. I don't know. I didn't plot it, but maybe the tire of the car, or maybe the door here. So it basically identified a single object, and that object take the space of true. Elsewhere, we have all the falses. Okay, so basically it's just a simple masking with 0 and 1 denoting the presence or absence of an object. Okay, question? Okay, so you can also provide batch of images following the very same procedure. So yeah, no, you can do this fairly quickly to processing a large number of images and providing all the maskings for each image. Okay, and this one, the third tutorial, so this one is interesting because someone, I don't know exactly who did that, but we have this amazing AI community. People are doing fantastic work with SAMS model. So someone fine-tuned the SAMS model based on some medical imaging data. And presumably they have trained this, fine-tuned this model on a very large medical data set, medical imaging data set. And they make this open source and host the model on Huggingface. It's called MedSam. Now you can take a look of their documentation. So actually, yeah, this leads actually to the paper, I guess. Someone analyzing in medical images, you can take a look at this archive paper. And this model, based on its claim, greatly improve the accuracy of segmentation using SAM's model on medical images. Right? So the medical image are very different than the common photos that we take in everyday life, right? So therefore, because the SAM's model, although they trained on 1 billion images, but presumably most of the images are not related to medical imaging. They are from probably daily lives scenes, maybe from YouTube or somewhere. So therefore, the SAM's model out of the box may not provide you much precision in segmenting medical images. Okay? So therefore, it's great to see someone fine-tune this SAM's model on large language medical images so that it can improve the precision. So here, we still download the model, and so this is called Wang's lab, is some researchers lab, and they released this version, the MAD SAM's model. Right? So we download model from Huggingface because this made open source. And here we load a pretty small image data set pertaining to breast cancer. And this data set has only, because we only use the twin set, they have the twin and the test set, we only use the twin set, it has only 130 images. Okay? Very small data set, but this data set has not been used to train to fine-tune the MAD-SAM model. Okay? So we'll take a look of how accurate the MAD-SAM model is in producing masking on this breast cancer imaging data. Okay. So let's load a single image. This image, we load the image from the data set. It looks like this. I don't know. No, I'm definitely not an expert in medical imaging. This looks like I don't know, maybe an X-ray image or maybe an ultrasound image. I'm not sure. Right? Okay. So first, no, the images come with the ground truth, so we know actually exactly how they should be segmented. Okay. So here we load the ground truth segmentation. Is basically a masking of arrays with number of 0 and 1. 0 means absence of the object, means 1 is no presence of the object. And then here we can quickly plot the segmented part of the image, basically this part. Okay, this is what the researcher is interested in. If you take a look of this part. Okay, so basically they want to carve out this part. Okay, identify this as the object in that image. Okay, so this is the ground truth. So let's see how well the MAD-SAM model can do on carving out this part, okay, from the original image. Okay. So here, there's a helper function to get a bounding box. Again, as we said, the bounding box is very simple. You just identify 2 points at the diagonal. One is the top left, the other is bottom right. And then there's other helper function for showbox and showbox in the image. They are already, we've already talked about those helper functions. So here we use the bounding box to identify this object here. Okay, this bounding box is not really well crafted because it's a little bit too big for the object, but that's fine, right? Because we will see how well the SAM's model perform, okay, to identify carving out this part of the object. Okay. Let's see. Okay. We did the same thing. We call the model, we process the data, and then we make the model. We use the model to make the prediction. Okay. And so this is a little bit different because the the MATSAM model was fine-tuned using a different loss function than the original loss function used by Sam's model. Okay, so therefore, we have to apply this sigmoid loss function. Okay, and then after that, we can show the predicted mask. Okay, so if you take a look at the predicted mask, so this is a predicted mask using the MATSAM model, and this is the ground truth. Okay, they are pretty similar, right? So the ground truth is a little bit more carved out at this point, a little larger probably than the predicted masking, but I would say the predicted masking is pretty good. Okay. Okay. Any question? So I see that Peachy asked a question. Oh, okay. RTBAX in the context of ultrasound likely stand for right breast as axillary, referring to an ultrasound examination of the right breast and axillary armpit area. Okay, so this type of ultrasound is commonly used for examining breast tissue and the axillary lymph nodes, which can be important in the diagnosis and the staging of breast cancer, as well as in the assessment of other breast-related conditions. Okay, great. So Peachy got this. Yeah, so there's a small hint here, right? RTB. So I was not too far off, right? So it is an ultrasound image. Great, great. Thank you, Peachy, for looking into this. Any questions? Okay, so this is amazing, right? Because the MATSAM model out of the box can make a prediction that is almost the same as the ground truth, right? Without fine-tuning at all. Okay. Okay, so we'll leave the rest. They are not really important. But finally, I want to show that you can and we can, each of us can fine-tune the model, the SAM model. Okay, let's take a look of how we can do that. Actually, it's pretty easy. So for those of you who are familiar with fine-tuning just means now we are going to use our own data set to retrain the model so that all the model weights, basically model parameters, can be optimized to address our specific tasks. Okay. So the model weights is just the model parameter, right? So basically we are going to change each of this, I don't know, 600 million parameters, right? So to make them better suited to address, to make predictions on our own data. Okay, so that is fine tuning. Okay. So, well, it seems like a daunting task, right? Because, well, now you have to basically calculate and optimize this, 600 million parameters on Sam's model, right? But actually, we said no, Sam's model is a relatively small model. It can fit into a single GPU, so we can use Colab to do that because Colab offers us a single GPU, right? Okay, so the setup environment, install the transformer, install the dataset. Dataset is not a dataset. Dataset is a package that use Apache data format to host the data, right? So that it can be easily manipulated by the model. And so this we also need to install this Modi repo. So Modi repo has some kind of customized loss function that are called by the SAM's model. And now we can load the data set. Again, we are just using this breast cancer data set. We use a very small data set because then we can train the model really quickly. Okay. But well, in reality, if you want to train your own model, you are probably likely to provide a much larger data set, right? Probably with thousands, if not tens of thousands of images together with the ground truth. Okay. Ground truth just means the maskings, right? For each image. Okay. So you need to have an image, and you need to have a pairing masking image that of the same size, okay, in order to train the SAMS model, okay, because the model is basically making the prediction using the original data, using the original image trying to predict the masking, right? So therefore, when you train the model in a supervised learning, you have to provide both the image as well as the ground truth masking. Okay. Okay, so here we load the breast cancer images, just as we said, 130 images together with their masking ground truth. So you can take a look of this. This is the image, and this is the masking. So they are a pair. Okay. Now we need to create, we are going to use the PyTorch. As we said, no, we really love PyTorch. In both in my deep learning, we exclusively focus on PyTorch because it's easy to learn, it has an uptake that is probably the most popular deep learning framework, surpassing TensorFlow produced by Google to be the #1 platform for building deep learning models. So yeah, people all the world use PyTorch and build tooling based on PyTorch. So we need to create a PyTorch data set. So we're not really going into detail of how to build a PyTorch data set. In my deep learning course, we spend some time talking about the nitty-gritty details about how to create a PyTorch data set. It's pretty actually simple. It only needs to have 3 properties to be qualified as a PyTorch data set. But well, we're not going to go into much detail about that. So this is basically the very simple. This is the step we create a customized PyTorch data set. So it only needs to satisfy, as we said, three attributes. The first one is you have to have an init function. The second, you have to have a len function, basically telling you how many data points, how many examples are in this data set. And third, you have to have a get item function, which is basically grabbing one random image from the data set. Okay, so as long as any class can satisfy the 3 conditions, it has an init function, it has a len function, it has a get item function. It is a PyTorch data set. Okay. So what we have is that we have 2, right? As we said, the data set needs to have an image ground truth masking pair, right? So this is the image, this is the ground truth masking, okay? And then we are going to fine-tune not on the SAM model, but on the medical SAM model, right? Because that is even better, right? Because we know that the MedSAM model has already been fine-tuned on a large number of medical images. So on top of that, we add a little bit more of data so the model can be better suited for our own specific medical imaging tasks. Okay, so that's always desirable than training directly on the SAMS model. Okay. So we get this medical MedSAM model. We create this data set, training data set with 130 medical images. And then we can test out how the data set performs. Basically, we just randomly pick one sample out of this data. Actually, not random. That is the first image from this built PyTorch customized data set. Okay, and you can take a look of the image. The image actually is in grayscale. It has only 2 dimensions, the height and width. It doesn't have a channel dimension because it's a gray image. It has only shade of gray, but not other colors. Okay. So we create a data loader. So the role of the data loader is basically grabbing randomly grabbing a batch of images from the formal data set and used to feed into the model. Okay, so that's what the data loader is doing. You can decide upon the batch size at this step. A large batch size is going to consume more memory, but usually it gives you better results. But well, remember that we have a relatively large model and we only have a single GPU, so you can't really afford a batch size of 64, right? So we are going to use a pretty small batch size of 2. Okay. And then what we are doing is basically we just provide 2 images at one time to feed into the model. And so therefore, the first dimension 2 just means 2 images. And then each image is a square image with 255 pixel as the height and 256 56 as the width. Okay. Any questions so far? Okay. And then we load the model. Okay. It's a pre-trained model, and we're going to fine-tune it. And fine-tuning, actually, when you do the fine-tuning, no, here you're only fine-tuning the image encoder. Okay, you are not really fine-tuning the other part of the model. Okay, because as we said, there are 2 parts of this model. The prompting part should not be fine-tuned, right? Because you don't really provide the prompts. Okay, so the original SAMS model explicitly tell that when you fine-tune the model, please do not fine-tune the prompting part, just fine-tuning the image encoding part. Okay, so therefore it set required gradients to be false for the other parts of the model. Okay, so you're only fine-tuning the image encoder, which take the majority of the model. Okay, about 600 million parameters. Okay. The prompt encoder and decoder, they are very small. Okay. To train the model, here we use the Atom as the optimizer, and call this customized sigmoid loss function from O9. And then the training itself is very simple. It's very simple. It's basically just following the 4 procedures in training any deep learning model. No, those of you who have taken my deep learning course know those 4 steps. The forward pass, basically feeding the data into the model, and then computing the loss function, and then do the back propagation, basically using the gradient descent approach to back propagate from the end of the layer to the first layer in order to optimize, in order to calculate the gradients, and then use the gradients to optimize the parameters. Okay, so any deep learning training follow exactly these 4 steps. Okay, so they are very much standardized. Forward pass, loss computation, back propagation, and optimization. Okay. Well, the tutorial asks you to train the model for like 100 epochs. Okay, so 100 epochs is actually, well, pretty small, because the more complicated the model is, the more probably epochs you want to take. Especially for computer vision models, usually we train the model for a large number of epochs, sometimes 500, sometimes 1,000. But well, no, this is a 2 example. So we train 100 epochs. So it takes really quickly because we only have 130 images, right? So I trained this model for, I stopped. I didn't really train for 100 epochs. I trained for how many? 73. And for some reason, I lost the connection, so the model stops. But it's okay. No, it trained for 73 epochs. You probably want to train more, but let's take a look of how the model performs after 73 epochs of training. Again, we provide the data, training data, and then we'll provide the ground truth labeling. Remember, when you use the model for prediction, make sure that you put the model into evaluation mode, okay? Because you are not training the model anymore, right? So otherwise, if you do not forget to add evaluation mode, the model may keep updating the parameter based on the new image that you provide, which is not desirable, okay? And then everything remains the same. You apply the sigmoid function, and then you take a look of the predicted mask. Look like this. It look actually better than out of the box. Right? Remember, out of the box, we use the model to make a prediction, and the boundary was not very clear. But now you get probably a more regular shaped boundary, and this is ground truth. Still, it's not the same as the ground truth, but I would say is probably better than out-of-box performance of the MapSum model. Okay, so you can try more, train more approx. Usually, when you train more approx, the model is going to perform even better. But of course, it's not guaranteed. You have to take a look of the loss, right? Making sure that the loss is still, in the long run, being reduced. Okay. Any question? Okay, so that's all I want to share today. Hopefully it give you a lot of things to play with, because it's just amazing, right? Out of the box, we get a SAMS model. We're able to access the model, use the model to make predictions. We can also fine tune our model just using a single GPU, right? I would say it's almost a free gift, right? And very powerful gift to many of you who are interested in designing your computer vision models and add an image segmentation or object detection capacity. Okay. And definitely, I think there's a tremendous usefulness in medicine. If later on you may get an internship, I don't know, in WashU School of Medicine or other treating hospitals, and you will say, well, now I know how to use your medical imaging data to train the state-of-the-art image segmentation models to help you automating tasks, right? People would be amazed, right? They'll say, wow, really? So I don't think most physicians probably never heard of a SAMS model. And of course, not really to train the model. But now you have these toolkits at your fingertips. You can just borrow the templates and start training your own models. Okay. Okay. Any final questions, comments? So I asked you to send you a notice. That no, we really want to keep our interest group as an active group, right? Active means that you regularly attend our meetings. It's not a major commitment. It's just attend and learn, and we only have this meeting once every 2 weeks. So you know the law of Facebook is that 99% of the people never used Facebook, right? They have this zombie what do I say this a zombie login username, but people never really use it or posting, right? We don't want our interest group like a zombie thing, right? We want to be very much alive, very much active, because we want to contribute, we want to learn from each other. So therefore, we make this kind of principle that unless you have some urgent issues that you cannot attend, you can always tell Yi and myself, but give us a heads up so we know what's going on. But otherwise, we would expect you to attend this live session, so that you can ask questions, you can keep an active learning mind. And if we do not hear from you and you you don't attend for 2 consecutive times, we'll move you out of the interest group, because that just means that you are not interested in active learning. And of course, you can still watch the YouTube recordings. Is open to everyone, right? And you know the web link. But well, to be actively engaging in the interest group is very important, right? Because that is our name. We are interested in learning this, so that's the reason why we can win, right? We spend 1.5 hour during the weekend, and we all need to sacrifice something, right? Because we have this protected time to learn from each other. Okay, so that is the rationale. Is by no means no penalizing anyone, because we just want to give you some motivation to learn from each other, because I think this is a fantastic place. It's a safe place. It's an active place. And there's no financial string or anything with this. It's completely free. The only goal is to foster learning. Okay, so that's the sole goal of having this interest group. Okay, so that's all for today. Any final thoughts or questions? And yeah, sure. Thank you. And yeah, you all have a fantastic evening, and we'll see all of you in 2 weeks. Bye, everyone.